Hello everybody, this is Mr. Molikash again. This is our video for week 6 in Math 172. Don't forget my email address is jsmolokach@johnstoncc.edu. This week we're going to go through what's coming up in sections 5.2 and 5.3 of your textbook, and specifically the identities that we'll be needing. And don't forget from last week that we have our sheet of trigonometric identities that we've been using. So we're going to break that out again for this week. There is something in this section here. It's called the power reducing formula, and that's not on the sheet, so I'll talk about that, and then we'll go through some sample problems for the written homework. Okay, so first off, here's our list of identities. Last week we were going through the fundamental identities, right? And the fundamental identities are those that are listed here for 5.1. These are called quotient identities in the textbook, but they're tangent and cotangent that can be written as quotients of sine and cosine or vice versa. And our reciprocal identities, Pythagorean identities, and even odd identities. So for this week in 5.2, we're going to be using the sum and difference identities. So this is what happens when you have two angles added together and you want to find the sine, cosine, or tangent of those, the sum of the two angles. You can also find the sine, cosine, or tangent of the difference of two angles when one angle is subtracted from another and you have a smaller angle. So these are formulas for that. They're very important formulas to remember, and for the sine and cosine at least, a teacher once told me a little cheerleading kind of rhyme that goes along with this. So sine first, then cosine, right? So it goes, for the first and second angle, it goes sine, cosine, cosine, sine, cosine, cosine, sine, sine. And you notice that I paused when I said cosine, cosine, sine, sine. And the pause is because the SIGN changes there, right? So if we're adding here, we subtract here. If we're subtracting here, we add here. Okay. There's the formula for tangent. But remember that from last week that if you want tangent and you already know the sine and cosine, you could just divide those. So you could do this formula divided by this one, and it automatically gives you the answer to this. But there is a formula for that that makes things a little easier. Okay. All right. Now there's in 5.3. There's these things called double angle identities, and so what happens is when you add alpha to itself, if you have alpha plus alpha, then you'd have sine alpha cosine alpha plus cosine alpha sine alpha, and there'd be two of them, right? So these are just special cases of when you're adding an angle to itself and you're doubling the angle, right? And so this is what happens with sine, cosine. The cosine has three different formulas, and the reason why there's three different ones is because cosine squared and sine squared have a special relationship in the Pythagorean identity. So, you can change this around to make it look like if you have the cosine and sine, you could use this version. If you only have the cosine, use this version. If you only have the sine, you can use this version. And again, that's just to make things easier. And then here's the one for tangent. And then there's half angle identity. So if you were to sort of work backwards, right? If this were the angle and these were the half angles, right? You could use this one and work backwards to find the sine of a half of an angle, right? When you do the square root, you're going to have plus or minus square root, and it's important when looking at these formulas that you choose the correct SIGN, the plus or minus, and that is all dependent on where this angle is. So if this angle, for example, is in the first quadrant, then the sine of that angle should be positive and not negative. If the sine of this half of an angle is in the third quadrant, then you would use the negative. And so the same rules apply for cosine and tangent. You have to go back and remember your unit circle and know which quadrant the half angle is in. Okay, and so that would determine whether you use the plus or the minus. Don't ever use both. You have to choose one or the other. Okay. All right. so that's our first item that we had to talk about. Next, we need to talk about what the power reducing formulas are, and what that is designed to do is when you go take Calculus 1, it's helpful to know the power reducing formulas to do some calculus. And in fact, there's some calculus problems that you can only do using these formulas, right? And they're not on this sheet, but they kind of are. And what I mean by that is that they use the cosine of 2 theta and either this version of the cosine of 2 theta or this version. And so what's happening is we're just going to reduce the power from a power of 2 down to a power of 1. So I'm just going to quickly show you where these power reducing formulas come from. So first thing I'm going to do is take these two red things and set them equal to each other. Okay, so let me do that. So this is the power reducing formula. Sorry about my terrible handwriting there. R-E-D-U-C-I-N-G, but for cosine. Okay, so the way that we do that is we have 2 cosine squared theta minus 1. That was one thing that could equal the cosine of the double angle, right? So what we want to do is be able to reduce the power of the cosine from a power of 2 down to some other cosine to a power of 1. So all I'm going to do is get this by itself. And so the first thing I'm going to do is add 1 to both sides, right? So if I add 1 to this side, that goes away, and if I add 1 to this side, I get this. And now we're going to divide both sides by 2, right? Okay. All right, so in the book, I think it's going to put the 1 first. It's like 1 plus cosine 2 theta divided by 2. Okay, so this is called a power reducing formula. And really and truly all it is the double angle formula rewritten so that instead of the double angle being solved for, it's the cosine squared is being solved for. All right? All right, same thing happens with sine. You can reduce the power of sine by setting the green thing equal to the double angle. And so I'll do that real quick. Let's see, I'll do that in black because I think the light green doesn't really show up too well. Okay, so what happens with that is we have 1 minus 2 sine squared theta, and that's another thing that can equal the cosine of 2 theta, right? So what we need to do here is a little bit more tricky because there's a negative sign, but the 1 is positive, right? So what we're going to do is subtract 1 from both sides, okay? And that cancels out, and then we'll have to divide by negative 2, right? We'll have to divide by negative 2. So then the negative 2's cancel out, and you get sine squared theta equals. Now, I'm going to be consistent and do this one like I did the one over here. So negative 1 divided by negative 2 is positive 1/2, right? And then a positive cosine 2 theta divided by negative 2 is negative cosine 2 theta over 2. So this is the power reducing formula for sine. Okay, now you'll never need to derive these in the way that I did, but I just want to kind of justify the reason why these aren't written on the formula sheet, because in a way they're already there. They're just not manipulated the way that I did here. So you will need these two formulas, okay, to do some work and on your next test. So notice that the right side of each equation here is exactly the same, except one's plus and one's minus, and that's kind of neat, right? So it's either 1 plus the cosine of the double angle divided by 2, and that's for cosine, and for sine it's 1 minus the cosine of the double angle divided by 2. And also, don't get confused here, right? The sine squared still has a cosine of the double angle. So what we're doing is we're exploiting the double angle cosine formula, not the sine formula, okay? And I realize this is a lot to kind of swallow right now, so do go back and rewatch this when you need to, when you're stuck on a problem. Okay. All right. So that's that. That's the power reducing formula. So now we're going to look at some sample problems for the homework. Okay. So this week, and we're going to look at section 5.3 first. And I have these labeled wrong. Actually, it's 5.2 and 5.3. So sorry about that. That's 5.2 and this is 5.3. But okay. So yeah, what we're going to do is we're gonna take a look at this angle sum formula, right? Angle sum formula, and in this particular exercise, it says find the exact value. What does exact value mean? It means fraction in simplest terms. It means square root simplified, no decimals, right? No calculator usage here, for example. All right, so we need the exact value for the expression under the given conditions. And you want to see examples 3 and 5 in section 5.2. Sorry about that. All right, so this is what we want to find right here. All right, so we have to go back to our formula sheet and remember what that is, right? Cosine of alpha plus beta. Remember what we said. If we're adding here, we subtract here. So let's just go ahead and write that out real quick. That is cosine, cosine, pause, and then sine. Okay, so that's something that we need to use to get the answer to this, right? Well, there's a couple of things that we already know. One is the sine of alpha is -3/5. So this thing right here is -3/5. So we can go ahead and plug that in right now. Similarly, it also tells us that the cosine of some other angle, beta, this is a different angle from alpha, but the cosine of that that angle is -3/4. I'll see if I can spit out my words right here. Sorry about that. Okay, so what are we missing? Well, we're missing the cosine of the first angle and the sine of the second angle, right? So for that, we're going to kind of need some information. For example, here it says alpha is in quadrant 3, right? So if alpha is in quadrant 3, then it's down here somewhere, right? The terminal side of the angle is down here. I'll be using directed line segments. So the length, all these lengths are positive lengths, but because of where they're located, in the third quadrant, I'm going to use a negative for the x coordinate and a negative for the y coordinate. So don't get confused. I'm not writing that the length is negative. I'm just saying the length is in the negative part of the x-axis or y-axis. All right. So yeah, the sine in alpha, the sine is -3/5. So remember, sine is opposite over hypotenuse. The hypotenuse is 5 then, and if this is our alpha, and really alpha is all the way around, but this is the terminal side of the alpha, the -3 would be the opposite, -3/5, right? So what do we need to do? Well, we need to figure out how long that is, because we need the cosine of it, and cosine's adjacent over hypotenuse. And so you could do the Pythagorean theorem, right? You could say -3 squared plus x squared, and that's the x coordinate that we need, right, equals 5 squared. And okay, so we can do that real quickly and get to subtract 9, and then the x would be either plus or -4. It's very important to realize that in an equation like this, that there are two numbers that could be squared to make 16, right? 4 or -4. Which one do we want? We want the -4 because we're in quadrant 3, right? All right, so since that's -4, the cosine of this angle is -4/5. Okay, so hopefully you can kind of see where I'm going with this. The same thing's going to happen for a beta, right? So beta is in quadrant 2, which is up here somewhere, right? So if we draw that, we get a different color pen here. Our beta is in quadrant 2. And the cosine of it was negative 3 over 4. So why did I put the negative 3 here? Again, this is beta all the way around. Why did I do that? Because the cosine is adjacent over hypotenuse. So we're looking for the opposite, right? We need to figure out what that is. And that's the y coordinate, right? So we could do the same thing that we did before, right? Negative 3 squared plus y squared, that's the thing that we're missing, is 4 squared. And, you know, we can quickly do this. We're going to subtract 9, get y squared to be 7, and so we need either the positive or negative square root of 7. So which one is it? You guessed it, it's the positive one, right? Because we're in quadrant 2. So we're going to choose positive square root 7 since we're in quadrant 2, and that makes the sine of this angle square root 7 over 4. Okay, great. So now what we need to do is simplify all of this stuff, right? We just need to do the math here. So, okay, negative times a negative, that's 12 over 20. 4 times 3 and 5 times 4. And you could cancel the 4's out, but I'm not going to because I already have a common denominator here, right? So I want to keep the common denominator. And then minus minus, that's another plus. This would be 3 square root 7 over 20. So the answer to this question is 12 plus 3 square root 7 over 20. And 12, 3, and 20 don't have a common factor, so this is the simplest version of that number. Kind of a crazy looking number, but this whole thing that I circled is one value. And what is it? It's the cosine of the two angles added together. Okay, which two angles? Alpha and beta. So if we put them on a third graph and added them together, this crazy number here is what the cosine of that angle would be. Okay, all right. So next item up for bids. Okay. Here's a question. It says find the exact value, right? So word to the wise here, whenever you see tangent inverse or cosine inverse or anything inverse with trig functions, that is an angle, okay? So what I'm going to do is I'm going to say this is cosine of alpha minus beta. This inverse tangent is some angle somewhere, and this inverse cosine is some angle somewhere, right? All right. So we got to figure out what the cosine of this thing is, and our formula from our formula sheet, since this is minus, we're going to add. And remember the cheerleader thing, right? It's cosine, cosine, sine, sine. If you have a problem where it's the sine or tangent, this is a different formula. So again, refer to your formula sheet. All right. So, well, we got to figure out then a couple of things, right? So let's take a look at this first comparison, right? This thing is our alpha, right? So what does that mean? That means that there's some triangle. There's some triangle, since alpha is the inverse tangent of 8 over 15, then that means that the tangent of the alpha is 8 over 15. So if this is alpha, then opposite is 8 and adjacent is 15. Okay, I'm going to save some time here so that this video isn't too long, but if you do the Pythagorean theorem here, you'll get 17 for the hypotenuse. So just do a squared plus b squared equals c squared. Now immediately, because you'll have all three sides, you know both the sine and cosine of that angle, right? So what's the cosine of this angle? It's 15 over 17, so that's what this is. And the sine of this angle is 8 over 17. All right. Now we could do a similar trick for the beta, right? I think you can see where I'm going to go with this. So at the risk of not being able to be seen here, I'm going to try to do this in green. So this is beta. So we're going to have another triangle. I'm hoping you can see this. Okay. Just checking my camera here to see if you guys can see this. So there's a beta angle, right? And we know that the beta is the inverse cosine of 3/5. So what does that mean? That means that the cosine of beta is 3/5. which means this is 3 and this is 5. Remember, again, cosine is adjacent over hypotenuse, right? And again, do the, a squared plus b, so you could call that b, equals c squared. This is going to turn out to be 4 if you do the Pythagorean theorem. So what does that mean? Well, the cosine of beta is definitely 3/5. And what's the sine? It's opposite over hypotenuse, so that would be 4/5. Okay, and now all we have to do is add all this together, right? So 17 times 5 turns out to be, I think, 65? No, 85? Yeah, 85. Okay, so 15 times 3 is 45, and 8 times 4 is 32. And we'll add this together real quick, and I think that turns out to be 77 over 85. And let's check real quick, that does not reduce. Okay, so if we took this angle and the beta angle got subtracted from it, we have a much smaller angle, right? We'd have a smaller angle, and the cosine of that angle would be this number, okay? So there'd be some other triangle where the hypotenuse would be 85 and the adjacent would be 77. Okay, so that's kind of how that works. All right, I'm going to try to skip ahead a little bit. I will tell you that in this kind of problem, you should do this is alpha and this is beta, and work out the sum formula that I did. And if you do that, it should work out to equal this. Okay, so that is just a real quick verifying the identity from last week. All right, so in 5.3, not 5.4, we have a whole different set of formulas, right? We have to do the double angle formulas, which I was talking about earlier, and also the half angle formulas, right? So in this problem number 11, let's see, I want to make sure that everybody can see everything. All right, good. So what we need to do here is make sure that we know the formulas, right? So we have the tangent of some angle in the second quadrant. So the tangent of that angle, opposite has to be positive, but adjacent would be the negative part, right? Because y is positive and x is negative in quadrant 2. So you would want to make sure that the 5 is not negative and the 2 is positive. Otherwise, you'd have positive 2 and negative 5, and it would be in the fourth quadrant. So that's important that you know that. All right. So then you do the Pythagorean theorem, right? You do a squared plus b squared equals c squared, and you're going to turn out to have your hypotenuse be the square root of 29. So immediately we know the sine of this angle, the cosine of this angle, and of course they told us the tangent, right? And I'll just leave that as 5 over negative 2. All right, so for part A, they want the sine of 2 theta, and the formula for that is 2 sine theta cosine theta. So what does that equal? Well, sine theta, we just found out, is 5 over square root 29, and cosine theta is negative 2 over square root 29, and this is 2 over 1, right? So if we multiply all the things across the top, we get 10 times negative 2, which is negative 20, and on the bottom, the square root of 29 times another square root of 29 is just 29. So there's the answer to part A. Okay. For the cosine for part B, you can use one of 3 formulas like I talked about earlier. Does not matter which one you use, you'll get the same answer however you do it. So I'll just do the first one since I already know the sine and the cosine. So that's cosine squared theta minus sine squared theta. So that is something squared minus something else squared. The something that's being squared here is negative 2 over square root 29. And the something that's being squared over here is the 5 over the square root of 29. All right, so when you square a number, it's always positive, unless you're squaring 0, of course. So negative 2 times itself is 4. Square root 29 times itself is 29. 5 times 5 is 25. Square root 29 times itself is 29. And so we already have a common denominator, and we get negative 21 over 29. Okay. So just a side note here, that tells me something about this double. If we doubled this angle, right, we're already in the second quadrant. If we doubled the angle, we'd probably be in the fourth quadrant, right? And there's evidence for that, because both the sine and the cosine are negative numbers. So that's not true then. It's actually in the third quadrant, because both cosine and sine are both negative. So if we doubled this angle, we'd wind up somewhere in the third quadrant. All right. For part C, I'll just go ahead and finish this off, and then we'll be done for the day. The tangent, there's a tangent formula for this, right? But I'm going to skip that formula, because I'm going to remember that I just do sine divided by cosine, right? So that is the first answer that we got divided by the second answer that we got. And so what does that make? Well, remember from earlier math that when you divide by a fraction, you multiply by its reciprocal, right? So the 29s immediately cancel out. A negative divided by negative is a positive, so you get 20 over 21. If you do the other formula and you put the 5 over negative 2 in for the tangent, it will still work out, but it's much more difficult than just dividing the answers that you already have. Okay, that's all that we have time for this week. But do remember my email address, and also the discussion board about asking Mr. Molikash, and I'm doing a better job, answering those questions. So don't hesitate to contact me if you need help. Thanks so much.